Hello, everyone. My name is Josh. I am here in an echo. Oh, cool. I'm a software engineer at BuildKite. Yay. Um, and in my spare time, I do some open source work, mostly contributing to Rails and Puma. Something I started doing like 2 years ago. And Puma is something that's very interesting to work on and contribute to, especially if all you've ever done is write, code for Rails and build products. So this is just me going through pretty much the code base of Puma from a very high level, just going down. Um, yeah, cool. Let's get started. Awesome. So I'm guessing most people in the room know what Puma is, but quick intro. So Puma is a rack compatible HTTP 1.1 web server for Ruby applications. So rack is pretty much an interface slash protocol, which most Ruby web frameworks and servers follow, basically make them compatible with each other. It was written by Evan Phoenix, released in 2011, and it's open source. So it's had quite a few contributors since then. It's inspired by Mongrel, which is another Ruby web server that came out in 2008, written by Zed Shaw. And it was a big deal at the time, I think. And this was like pre-Rack, and there weren't many, cool things around at the time in Ruby land. One of the cool things about Puma is it still to this day utilizes Mongrel's HTTP parser that's written in, I never know how to pronounce this right. It's either Regal or Ragel or Raggle, but it's pretty much a kind of meta language that's used for creating state machines. And it's pretty cool. You basically create your state machine in a very declarative language, and then you can spit that out basically in any other language. So Puma, for example, defines its parser in Raggle and then compiles it out to C and Java to maintain compatibility with Truffle Ruby and JRuby. Um, and yeah, Puma is built with parallelism and concurrency at the forefront, and it's a very performant and stable web server, which is why it's also the default for Rails as of Rails 5, I think. So I'm guessing the main way that most of us have probably heard about Puma is running this command here, starting up our new Rails app. And I'm just going to go and do that very quickly. So this is a brand new Rails app that's actually pointing to Rails main. If we start up this command here, these log lines at the very start are coming from Rails itself, and then everything else is Puma. And I just wanted to go through like how Rails integrates with Puma and how it actually does this. So if you go look at the actual executable that Rails runs, which is this one here. So I'm not going to go down all the way through this. So Rails uses a gem called Tor for building its CLI, but I'm just going to fast forward to the actual server command, which boots up Puma for us. Actually, before I go too far, I'm going to say there's a lot of code in this talk. So if I'm going too fast or if something doesn't make sense or if you have a question, just feel free to interrupt at any time. Cool. So the entry point really to where Rails boots a server is this server command start method. We can ignore all of this stuff here. It's basically just some setup, setting up some signal handlers, creating some directories and dev caching. But you'll notice that it calls this super method here. And if you go look at what it's inheriting from, Rails has this rackup server class, and not super important, but I think as of like rack 3 or something, they split up rack up into a separate gem, which is why we have this conditional require here. But we're just going to ignore that for now and just go dig into what this server actually looks like. So if we go look for the super method that we need, again, we're just going to ignore all of this sort of setup code, and the real important stuff is over here. So that's pretty much where our server starts, our Rails server slash Puma server. This server method we'll see is coming from here. So it's got this handler class, and it's trying to get the actual server. I can tell you that this, unless you've configured it otherwise, this server option here is going to be Puma itself. And if you go have a look at that handler, This is actually coming from, and you'll see up here, from the Rackup gem itself, as of Rack 3. And Rackup comes with, in order for a server to be compatible with Rack, it's expected that web servers create an interface, which is called a Rack handler. Rackup itself, I think, comes with two adapters kind of built in just for the WebBrick and CGI web servers. Any other server is expected to provide their own. So at the very start here, what this is doing is just looking at Rackup itself and saying, hey, do we have the handler for these servers? And it's not going to have one because Puma doesn't come built in. But what it's going to do is it's going to require this file here. And again, it's all built on convention. So Rackup expects the web servers to have their handler at a specific path. And what this is going to look for is pretty much something like rack slash, can't type, handler slash puma.rb, or rackup slash handler slash puma.rb. And if we very quickly jump into Puma itself, and if you've got the Puma gem installed, and this file here is going to be in your load path. And this is pretty much the handler that Puma creates so that Rails can actually boot it up. So if you go look for that run method that was getting called before, this is pretty much the entry point. I'm just going to zoom out a bit and hopefully you guys can still see the code. But yeah, this is pretty much Puma's entry point, coming all the way from Rails. And I think we all know that like you don't have to boot up Puma through your Rails server. Like you can actually just boot up the Puma executable itself. So if you do bundle exec Puma, for example, you're going to see the same output, but just without those Rails log lines. And if you inspect the Puma executable over here, it's pretty simple, but essentially it creates this new CLI instance and calls its run method. And if you go inspect that, we're going to see that it's a very similar setup. If you put these side by side here, cool. So you'll notice that both of these are pretty much how you start up Puma in just two different ways, either coming from the handler or from the CLI directly. And you'll notice that they both have this launcher instance that they call run on. So the launcher is pretty much the entry point into Puma itself. Just going to close these over here. And if we inspect its run method, that's pretty much where Puma starts, where the actual HTTP server starts booting. Let's go look at where this runner is coming from. So there's a comment here saying this blocks until the server is stopped. And if we go look at where this runner is initialized, you'll notice that it could be one of two things, so either single or cluster. And you'll notice that when we booted Puma up before as well, and you've probably seen this a few times, it said, Puma's booting up in single mode. And that's pretty much one of the two modes that Puma comes with. So by default, it boots up into single mode, and single here implies a single process, as in like an OS process, which means a single server and a single thread pool. What that looks like, if you just lay it out in a diagram, well, that looks terrible on the screen, but we've got our launcher, which is our entry point into Puma. We've got this runner class, which could be either a single or a cluster. And then you've got your server, which is an actual thread that runs in the background, handling all your requests. And then the server manages a thread pool. And they're called worker threads, but those are the actual threads that handle the work of dealing with all the requests, handing them over to the app and returning the responses. And the other mode that Puma comes with or can be configured with is cluster mode, which is what most people run in production. So here, cluster implies a cluster of processes, also referred to as workers, which means you get a server and a thread pool per worker. These can be configured a couple of ways. Using the CLI, you've got the W flag. You can use the Puma DSL with the workers method, or it's pretty standard to configure it with one of these environment variables. Rails actually uses with concurrency by default. and that'll basically configure cluster mode for you in production. Maybe I'll zoom this in. But that's what cluster mode looks like. So we've got our launcher again, we've got our runner, but here it gets a bit different. So the runner in cluster mode is sometimes referred to as the master or the master process. And Puma forks or uses Ruby's process.fork or kernel.fork, which uses the fork to system command to basically spawn two processes from the master. And those are the worker processes according to the number you've configured. So each worker is its own unique process, which has its own server, thread again, and manages its own thread pool. Yeah. Cool. Let's go back to the code and have a look at what it actually looks like to run one of these. So we're going to start with single mode. To go have a look at single mode's run method here. Is that zoomed in enough, I guess? Yeah, cool. Cool. So I'm gonna skip through stuff that's not important, but here we just log to stand it out, saying that we're running in single mode. Load and bind is a method that that's looks very simple at the surface, but there's a lot going on there. So the load part of it is loading the actual application into memory. And then bind is Puma taking wherever you've told it that your sockets are going to be and binding the actual launcher onto that. So it starts listening on those sockets as soon as it's loaded the app into memory. Plugins.fire background is just firing some, booting up some startup threads to fire off some events to plugins that you can configure with Puma. These two, launcher.write state and start control, are related to the control server. So Puma lets you spawn a separate process alongside Puma itself, which you can use to actually control the Puma process, either via the CLI itself or via like a TCP port. And that's like an optional config that you can choose to run. I've never actually tried to use that myself. But here is where the crux of the actual request response handling is. Okay. Sorry, just going to reconnect. Cool. Yeah. And Puma goes ahead and starts the server in single mode and then starts running the server. Let's go have a look at what that actually looks like. I am, no, okay. Oh, good. Cool. Awesome. So this is the server, the thing responsible for actually doing all the work. One of the first things it does at the very beginning is start up its thread pool. So that'll be according to the number of threads that you've configured Puma with. I think it defaults to a minimum of 1 and a maximum of 5. And Puma will scale the thread pool up and down as requests come in. And the kind of layout I showed you before was kind of a simplified version. So in addition to the actual threads that handle all of your requests, Puma actually spawns a few other threads internally to manage things. And one of that here is this reactor thread. So reactor is a term I think quite commonly used in like event loops and such. And usually what it does, it basically listens to a piece of IO, like an IO object, like a socket or something. And whenever there's data to be read from it, it reacts and it does something with it. It's quite similar in Puma, but slightly different. So I think I got a slide on that. So yeah, so this is related to the queue requests method, sorry, DSL config that's enabled by default with Puma. So if you've got this enabled, Puma spawns up a reactor thread which is responsible for buffering incomplete requests. So what that means is whenever Puma gets a new connection and a new request, it's only going to start processing that if the entire request has come through. So if the entire, like all the data of the request matches the content length header. If it isn't ready, Puma basically, or at least the worker threads, they hand that connection off to this reactor thread and basically tell it, hey, like we've got an incomplete request. You just keep listening to that, and when it's ready, give it back to me. It's enabled by default. One, I don't know, caveat or side effect of it is that when it's disabled, Puma can't support keep alives anymore as well. So when it is enabled, as data comes through, Puma will keep the connection open, and it has a persistent timeout of, I think, 10 seconds or something like that. But if you turn off queue request, Puma has no choice but for the worker thread to handle the request as it comes through. That makes you susceptible to slow client attacks. So if you've got a client that opens up a connection and has large gaps between when it sends through data, your thread is basically monopolized by that request, and it can't really accept anything else, which keeps your server quite busy. Cool. Going back to the code. These are two other threads that the server spawns. So one's called the Reaper thread and the other the Trimmer thread. The Reaper is responsible for killing off dead threads. So if a thread is no longer live, this Reaper, I think it runs every 10 seconds or so, based off of whatever that reaping time is, which has a sensible default. It's going to go ahead and just kill all those dead threads and spawn up new ones. There's another thread responsible for trimming the pool. So unless you configure the thread pool with the same min and max, so if you say, hey, I need a min of 1 and a max of 5, like I said before, Puma is going to scale that up as needed, but it's also going to scale it down, when your server is not as busy, and that's what that thread's responsible for. I'm going to skip over this bit. It's just some config stuff, but by default, the server runs in a background thread. So all this method does is start up everything the server needs, create a thread for the server itself, and then it'll block until you either send an interrupt signal or whatever to kill the thread off. So this handle servers method is basically the main, I want to say, event loop. It's quite a heavy method, but if you condense this down, it's pretty much like the start of this is pretty much just doing some config setup, not very important. That's our main loop over there. And everything after that is basically handling and managing state if the server happens to shut down. In other words, if you exit the loop. And if you go look at the loop, it's basically based off of this status state. So as long as that's not set and telling the server to stop or halt or whatever, this loop's going to keep running. And it's quite simple, really. It uses this IO select method, which uses the OS's select to command. And all it's doing really is you can pass in 3 arguments here. All of them are meant to be arrays of IO objects. The first argument being objects that are meant to be written from, if you need to listen on any errors, IO errors. And then the last argument is the timeout. So this is a blocking method, and it's going to block and wait and listen to those sockets, basically waiting until there's any data to be read from them. And if you look at the timeout code, if we're in the process of shutting down, so if we've started off this loop and the state's told us to shut down, we set a timeout of 0, which means we return immediately, and then we start the shutdown sequence. Otherwise, and this is a pretty new feature, you can configure an idle timeout. So you can tell Puma, hey, if you haven't handled any requests in like a minute, just completely shut down. So this is pretty much going to block until one of those 3 things happens. Either there's some IO that's ready to be read from, we're shutting down and we've timed out, or we've timed out because we haven't received any requests in a specific amount of time. And all of this is again just managing the idle timeout feature and shutdown logic. But once we've actually got some data that's ready to be read, there's two weights here. That's pretty interesting, I think. So Puma only accepts as many connections as it can handle. So it's if you've got 5 threads, at any given time, you're going to have Puma's only got that process is only going to be handling 5 connections. Yeah, and this is despite having sorry, a caveat to this is that reactor thread we mentioned before. So if a thread becomes available, a connection comes through, it's not ready, and we've handed it over to the reactor thread, we can still have a lot of connections piling up in that thread over there. But for complete requests, Puma will only accept as many as it can handle. And this other weight here is a pretty interesting one. So this is a newish feature that came out in Puma 5 that the folks over at GitLab contributed. But what you might have noticed up till now is we could have multiple processes. All of them have a server each, but we've only got one socket, right? Where all these processes are listening onto. It could be one or more, but they're all listening to the same socket. And what that means is that there's no load balancing happening. They're all listening to this one socket, and whoever gets there first is going to pick up that request and start processing it. So that could result in scenarios where you have one worker that's extremely busy because their 5 threads fill up, a thread becomes available, it picks up work immediately, thread becomes available, and it just keeps going. And what the folks over at GitLab found is that if you inject a very small timeout to workers that are occupied like at all, that gives priority to a worker that's literally just sitting around doing nothing, right? So if you take 2 workers, for example, and this worker's got 4 threads busy, it's going to hit this wait, and it's going to go, okay, I've got a non-zero amount of busy workers. So I'm just going to wait for a second, and then ideally the other worker that's completely free gets to this point and picks the request off the socket. Cool. And then we actually have the code that reads the request off the socket. So this could raise because again, we're all reading off of the same socket. So it could be possible that 2 workers get to this point at the same time, and one reads before the other. But if we do manage to read a request off of it, it's wrapped in this client object and handed over to the pool for it to do its thing. And that's pretty much it. Like that's the core of of the request handling process. Now that we've had a look at the single runner and how it manages its server, you can have a look at cluster. Oops. Very quickly. So cluster mode's quite a bit different from single mode. Like I said, it's multi-process. This cluster class is referred to as the master, and we have our child processes spawning off of it, which means that it needs to do a lot of management, right? So this is the master process or the supervisor. It's going to have all of these workers doing their own thing. And it's kind of responsible for keeping them in check, making sure they're alive and all of that stuff. So again, pretty heavy method, but it's essentially doing a bunch of setup at the beginning. I thought I'd touch on this condition here. So Puma has this feature called preload app. Yeah, preload_app. What this does is it loads the application into memory in the master process before it starts forking your workers. The reason being is there's an OS level optimization called copy on write, which happens when you fork. And what that means is when you fork a process for the first time, it's not actually going to duplicate the memory for the child process as well. And you're essentially going to get 2 processes pointing to the same region of memory until the child process starts writing to those pages in memory, right? So Puma takes advantage of this with this feature. What that means in the context of something like Rails is if you boot up your Rails application once in the master process, and then you start forking your workers off of it, all kind of like immortal objects like your Rails configuration, your initializers, all stuff that you write to once on boot, and then you only read from there onwards, is not going to be duplicated in memory, and you're going to save a ton of memory when you start spawning 10, 20 workers or whatever that makes sense for the number of cores you have. So this was meant to be enabled by default in Puma v5, but there's a bit of a bug where it only actually got enabled by default if you used the environment variables to configure Puma, which is not a good thing because now it's a bit of a gotcha for especially large applications where people might not know if they're actually running this or not. So it's probably a good idea to go check this in your configs as well. But there's a patch in Puma v7 which will enable it by default. So you want to make sure that your application is actually fork safe, especially if you're spawning threads at boot time. Forking a process while there are running threads is sort of considered undefined behavior, and sort of anything could happen. So you're meant to kind of responsibly shut those threads down before the fork process happens, and then restart them in the child process. Oh, cool. Sorry, I forgot I had an image of what copy on write looks like, but yeah, you got your memory blocks in region, you got your parent process. When you fork a child process, they're still reading from those same pages, memory pages. And then when you actually write to one of them, that's when it actually duplicates that portion in memory. Cool. Yeah.
Just clarify, you mean reading memory of the process that's about the logic, the code that's running, that's the memory, right? Or you mean some data?
Yeah, the code that's running. So that'll be your actual application and Puma itself and everything. Yeah. Cool. So if I preload in, I don't know when this was decided, but it seems to be like another unwritten convention somewhere. But if you have any threads with a local variable set to fork safe, that kind of tells Puma, hey, we've taken care of these threads, don't worry about them. But if there are any threads that aren't marked as fork safe, Puma just keeps track of them before, loads the application into memory, and then afterwards, it'll see which of those threads are still hanging around, and it'll log out a warning if you use preload app saying, hey, we found these threads, you're using preload app and you forked a process off of it. It's probably not a good idea. Go have a look at what's happening. If you're not using preload app, Puma doesn't actually load the application at this point, but it will after it's forked all the processes. And when it boots up the actual workers, the workers will individually load their own applications, which again means you're basically doing the same thing in every single process, which is a lot more use of memory. Cool. Setting up a bunch of signals. Puma utilizes io.pipe a lot, which basically uses OS pipes to communicate between processes. So pipes are, I think they only, you can only communicate one way with them. So when you initialize a pipe, you get a reader and a writer. And usually what you do is you pass off, you hand the writer to your child process and you hold on to the reader, and then your child sends messages to you telling you like keeping you up to date on its status and stuff. So Puma uses this pretty heavily in cluster mode to communicate between the parent and child. Cool. We're just going to skip through all of this, just a bunch of config stuff. And then this is where Puma actually goes ahead and spawns those workers. All this code isn't important, but it's basically getting a diff of how many workers we currently have versus how many we should have, which at boot time is going to be 0. So the diff is going to be the max. It's going to iterate through that and spawn the actual worker. And here is where you'll find the actual fork command that Puma uses. So if you haven't used this before, the code inside the block is only going to run inside the forked process or the child. So inside the child, Puma goes ahead and creates a new instance of a worker. I'm not going to go into that code because it's pretty much the same as what we look at in single mode. So you get a worker, they've got their server and their thread pool. So it's basically like multiple processes doing what you would see in single mode. Cool. And then going back, after Puma spawned its workers, it starts its main master loop. So again, the master is responsible for keeping all of its workers in check. And the core of it is just this one condition here. So this read is the reader end of one of the pipes that Puma initialized above. And it's basically just sitting there waiting to hear from the workers, right? So it's another blocking method. You'll notice that we also pass a timeout into this. And that's just to make sure that we keep a regular check on what the workers are doing. So we don't want to sit around waiting permanently, just waiting to hear from a worker. So it'll do that until it reaches its next check timeout. But otherwise, if it does get a message from a worker, which could be a couple of things, like for example, if the worker says, hey, I just booted up, if that's a new worker that spawned, if it gets an external term. So if I, for example, just go grab the worker's PID and send it a SIG term, the worker's going to tell the master before dying. And yeah, a few other things that we don't really have to go into. But this main loop is pretty much just Puma managing itself, or the cluster managing itself and its workers. Cool. I'm a bit over time, but I think I'll stop there. That's what I would consider the surface level of Puma. So it's like I said, it's like I didn't know what any of this code did when I read it for the first time, like zero, and pretty much had to read every single method's documentation and learn about all these OS level commands and all of that. But it's a really interesting code base, a really interesting project. There are lots of cool features, and yeah, it's just a really nice piece of Ruby history. I've added some references to things that I recommend reading if you're interested in this sort of stuff. But otherwise, that's it from me. Thank you. Yeah.
When we have the thread pool with minimum and maximum thread, which are different.
Yeah.
How Puma decides when to steal those active threads?
Yeah, good question. Just a timeout. So I think you can configure it as well in the actual DSL. I don't know what it's called off the top of my head. Yeah, sorry, I can't give you the answer, but yeah, it's just a timeout. So you just say, hey, if if we haven't been busy for X amount of seconds, if there are any free threads just sitting around, just go kill them off until we're down to the minimum. Yeah.
The new feature to balance the load better in the cluster, is that enabled by default?
Yes, that's enabled by default as of 6.2 or 6. It's a very small timeout, like 0.05 0.005 seconds. Yeah, I don't know if there's a better way to do it. Like I was quite surprised that they went with that first. Yeah, it's nice, right? Yeah. 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 I guess the downside of it is if you do in fact have like if you're decently busy most of the time, then you're kind of waiting for no reason now. But yeah, if you kind of have bursts of requests, I think is when it makes the most sense, which is what GitLab said they usually run into it. Yeah. Yeah. Oh, this is Zed. And I think it's the GitHub theme. Yeah, theme selector. Sorry, I won't use this. Yeah, GitHub doc is what it's called. Yeah. Yeah.
What's a dead thread or a dead work that it's rigged? What does it mean if it's dead?
Could be for like actual code in your Rails application.
Too long.
Yeah, like yeah.
Like a
timeout or something like that, like for your request.
Yeah, could be a timeout, could be a crash, could be there's a rack timeout gem, which a lot of people use, and they use that. They basically say, hey, if we've hit the timeout, kill the actual thread. I don't know the reason behind it, but it's supposed to be like a clean slate, so you just kill off that old dirty thread and then start up a new one. Yeah, yes.
So this reactor thread is the one that's waiting for the rest of the data to come through.
Yes.
And there's only one of them.
There's only one of them. It doesn't actually, I found this interesting and I thought it was a bug, but it wasn't. But the worker threads actually receive the connection the first time and they try to eagerly read off of the socket. If it's ready, it'll process it. If it's not, then it hands it over to the reactor thread. What I thought the bug was in the docs, it says, the reactor thread does blah. And I was like, oh, why is the worker thread accepting it the first time? Why isn't the reactor thread doing that? And the reason is because of that first wait we saw. We wait until there's at least one free thread. So the thread's doing nothing anyway. So it might as well eagerly read the request. Yeah.
So wait the whole 10 seconds until the rest of the data comes through.
The reactor thread?
Right.
No. So it's going to hand it over and then move on to the next, like sit or wait for the next request to come through.
And then check the content information.
Yeah, pretty much. Yeah. Yeah, all that like lower level code is in a whole other class, and there's a lot of interesting stuff in there, a lot of IO methods, if you're interested in that. Yeah. Yes.
Is there a maximum number of processes or is that?
That's a good question. I don't think so. I think you probably don't want to try finding out. I don't know if there's a limit. Yeah, that's
Eventually operating.
yeah. Also, like I recently I've been working on a lot of its restart features. So there's 3 types of restarts. One of the most commonly used ones is called phased restart, where it gradually kills off workers and starts a new one. So it'll kill worker 1, start worker 1, like that. And if you have like 100, even at like 30 processes, that takes ages. So you're kind of losing the benefit of doing that. So yeah, I wouldn't recommend too many. Yeah.
Does that conflict with the preload app setting?
Yes, that's a very good. So phase restart isn't compatible with preload app. Yeah. There's another type of restart called refork, which is Puma actually introduced the refork concept before Pitchfork, which is completely based off of that. But yeah, that's something that's getting a lot of attention recently. I've got a few bug fixes for that, but there's actually quite a few people using that. So the idea being you preload, you fork your first worker, and then you fork all your workers off of that. And then you say, hey, after you've handled 10,000 requests, kill all of these workers and start forking new ones from this to basically increase your copy on write efficiency. Yeah. So once you've handled a lot of requests, you probably loaded up a few more classes and methods and memoized a few more things that are probably read only. And yeah, get a lot more efficient off. Cool. So awesome. Thanks, guys. Oh yeah, sorry. Oh, this is something I'm not qualified to speak on either. I think the simple way to say it is it's just another file. It's just another file descriptor. Hopefully Ryan can correct me on that. What do you think, Ryan? Yeah.
Yeah, it is, yeah. But it's not exactly like a file. You can't see it.
No. Yeah. I just picture it as a file. So when you think like reading and writing data, like the literal request that you make, like the body and the headers and everything, I just like visualize it as being in a file and then you're reading off of it. But
there's multiple writes to the same file, right?
There's multiple, yes.
So how do you distinguish? So they come like
So kind of to make it like you can have multiple threads like waiting on it, and then it'll pick which one.
Also depends on like what type of socket. For example, if you run Nginx alongside Puma in production, usually you would configure it with a Unix socket, like a local socket. So Nginx handles, buffers the request, writes to the socket, the Unix socket, and you read off of it, or it could be like a TCP socket, TCP over SSL or whatever. Yeah.
So it's like a file, but there's like a small file split in file.
That's all taken care of.
So every connection is its
Ah,
own file,
yeah.
and so the listening socket is its own file.
So there's benefits to using Linux socket where it's local in memory, which we use TCP socket, there's no way of TCP, extra packets for TCP connection. But from operating system level, at the very basic, I'm talking Linux, not considering Windows, sorry. Or Mac for that matter, everything is a file. So it's in memory file. A very crude example, and please don't beat me for that. It's like using this. It's a pub sub kind of. It's a very crude analogy. I'm trying to make their analogy.
I think that's it. Okay.